crosses a height of 30 meters. So when it crosses that 30-meter height, you can calculate the UG using MGH. And again, don't use the 20 meters. That isn't how far it's fallen, okay? It's how far it is above the ground. So then you can find your UG, right? And then your UG plus your kinetic has to add up to 4,900, okay? So then on D, when it lands, how much kinetic energy does it have? Oh, 4,900. How much potential energy does it have? 0, okay? Cool with that. So on C, do me a favor. On C, you should have two answers, the kinetic energy and the potential energy. Make sure I know which one is which. Just don't write down two values and expect that I'm going to know what they are. So on 3C, tell me which one is the UG, tell me which one is the kinetic. Okay? Just don't have two numbers written down. Now, on 4 with the arrow. Okay? So on 4, it's going to be the same idea. But this one, if you wanted to set up a chart, you could actually have like a third column. So you're going to have energy stored in the bow, you're going to have gravitational potential energy, and you're going to have kinetic energy. Okay, so from this one, if you wanted to set up a chart, okay, you'd actually have 3, because if you visualize this, you're going to pull this thing back, you're going to do work. I've given you the force, I've given you the distance. So you can find the work that you're going to do. And that's storing energy in the bow. So that energy in the bow, when you take 201 times 1.3, so somebody take 201 times 1.3. Should get 2 something.
261.
261. Okay, I call it 261. Okay? So what that means is that when you're holding this bow back, right, you've stored 261 joules of potential energy in the bow. Okay? So that's like me pulling down the lever on the marble launcher. So if you, on a small scale, right? So you're doing this, you're pulling this down. I've stored potential energy in the bow, right? So everything else is going to be 0. I release the plunger. What's going to happen to the energy stored in the bow? It's going to change into kinetic energy. So then so at that point, I'm not going to have any energy stored in the bow. I haven't, it isn't above the ground yet, so I don't have any UG. So my kinetic energy is going to be 261 joules. So now that I know my kinetic energy, then I can find my velocity. So your velocity on number 4B should be around 40 meters per second. Okay? Around 40. Now, when it reaches its maximum height, so I'm going to release this, boom. So when that marble reached its maximum height, how much potential energy did it have?
Wait, 261.
261 joules. So I went from potential energy in the bow to kinetic energy to 261 joules of gravitational potential energy. So it's just, I'm just shifting from 261 here, energy in the bow, to 261 joules kinetic energy, to 261 joules of gravitational potential energy. And it all starts with the work that I do at the beginning. So that maximum height should be around 90 meters.
You're not going to cut us off where we don't have a chart, are you?
Not as long as your answers are right.
See.
Now, here's the conceptual thing that I want you to get on number 5, okay? So here's what I want you to get on number 5. Is that this thing is 2 meters above the ground, right? So here's what I want you to think through. It's 2 meters above the ground. Because it's above the ground, what type of energy does it have?
Potential.
It has UG, right? It has some type of UG. Now, if I just drop it, what's my initial kinetic energy going to be? Zero, right? I'm not going to have any. But here's what's different. On this one, instead of just dropping it, I'm going to throw it down, okay? So since I'm going to throw it down, it's also going to have, it's going to have UG, but it's also going to have some kinetic energy, right? Call that KT naught, my initial kinetic energy. Now, when it lands, okay, when it lands, does it have any UG? No, because it doesn't have any height. So these two values here have to add up to the final kinetic energy, okay? So, now, here's the contrast. If I just drop it, it's going to land with a certain velocity. If I throw it down, what's going to happen to the final velocity? Is it going to be bigger or smaller than if I just drop it? Bigger, because it's going to have UG and kinetic energy. Okay? Now, here's the thing to look at. If I throw it up in the air and then let it fall all the way down, that's going to have the same kinetic energy as if I just throw it straight down. Because kinetic energy is a scalar quantity. Which direction I throw that ball doesn't matter. If you look at that initial kinetic energy, the direction that I throw it, whether I throw it at an angle like this, whether I throw it down, whether I throw it up, whether I throw it horizontal, doesn't make any difference. Okay? Does not make any difference. That value of kinetic energy is going to be the same no matter which direction I throw that ball. So what that means is that if I throw it, no matter which direction I throw it, it's still going to land with the same final kinetic energy. Whether I throw it down, throw it up, throw it at an angle, throw it horizontal, doesn't make any difference. Okay? It's still going to land with the same amount of kinetic energy. So, your answer to 5F should, on a weighted GPA, would be pretty good. Okay? On number 7, every answer on number 7 should start with a 1.
What's the top U on the chart?
Which U?
What? The top one.
That's energy source of the bow.
Yeah, for you just said.
Yes?
You had
Why
negative
can't you
3
use,
for the 100
like, the
kilograms.
V naught squared plus
100
2GH
kilograms
equals V
minus
squared? Why
3
can't you use that to
minus
find
For which problem?
for 7C and
Because right in this
6?
one you just said
Hold on, for what?
you have
For
500
6
milliseconds
and
per
for 7C.
You can, but you have to know which acceleration.
For 7C, the final.
Yes, there's more than one way you can do this. I just looked at it from an energy
I
perspective.
feel like I still check.
Okay?
But like I get confused on like
Either.
when
I
you're
just did
like
this.
just any velocity plug it into
Hold on.
kinetic energy.
Okay, you're talking about two different problems. Pick one.
Both?
No.
Should we go over both?
Which one?
7C.
Okay. So on 7C, here's, if you're going to do final velocity of the rocket at the point the engine is shut off, okay? So you could use F equals ma. Okay, if you wanted to. It's a god-awful amount of work.
Okay.
You could use F equals ma. You know the net force, you know the mass, you can find the acceleration. Okay? It's a god-awful amount of work, but you can do that. And then you could use V squared equals V naught squared plus 2AD. And set the initial velocity of the rocket to be 0. Use that acceleration, and you know the distance. And you can do it that way.
But don't do it that way.
Well, you can. If you're old school F equals ma, you can do that. But it's just a lot of work. But my point on 7C is that, look, you already know what the kinetic energy is, and kinetic energy equals 1/2 mv squared, so it's just easy to take the kinetic energy and use that to find the velocity, then go through and finding F equals ma and then plugging it into that equation.
Is the change in kinetic energy the same as kinetic energy?
Yes, because change in kinetic energy equals your final kinetic energy minus your initial kinetic energy. What's your initial kinetic energy?
So,
Ellie?
Zero?
Yeah, because it's sitting here.
Okay.
So the change in the kinetic energy is going to be the same as your final kinetic energy, which is the same as the work that was done. So there is more than one way you can solve these problems. In this situation, the energy aspect is just going to be easier. Yes, Aiden?
You go with number 6.
Yeah. Same idea. So how I got the idea for number 6, I was actually in middle of the outback of Australia, and they had like, it was like kind of like the Kansas State Fair.
yeah. When did you go to
Australia and
Australia?
Africa?
Okay. Huh? What?
Australia and Africa?
When did you go to Australia?
It was the summer of '97. So a good friend of mine that I met from when I was in Africa, Tim Buckley, was from Australia, and he was teaching at the same school that I was at. He was back in Australia at the time in Alice Springs, and Alice Springs is like in the middle, literally like the middle of the outback. And my dad had died in October of '96, and I just needed to get out, so I just took off and spent like a week in New Zealand, and then spent like 3 weeks in Australia.
Dang,
So
that's cool.
just said, I'm out, see ya, peace out, get back, yeah, so. Oh,
Yeah, let's go to Australia. After finals week.
there you go. Okay,
Over
so here's the deal. So there's a couple of ways you can work number 6. If you look at it from an energy perspective, when this car is being held up, how much energy, what's the only type of energy that it has? Right? Right? Now, when it lands, what's the only type of energy that it's going to have? Kinetic. So I can set the UG at the top equal to the kinetic energy at the bottom, right? Okay? True.
True.
So UG is going to be mgh, and my kinetic energy is going to be 1/2 mv squared.
Cancel those
So why didn't I give you the mass of the car?
because you don't
Because
need
it
it.
cancels.
Because it cancels out of the equation, right? Do you know how fast you want the car to be moving when it lands?
Yep.
Yes. You know what g is?
Yeah.
Yes. Solve for height. Okay? Now, if you wanted to, okay, you could go old school and you could just use that equation. Okay? Because your initial velocity is going to be 0. You know your final velocity. You could do it that way. So if you're old school, you could work number 6 just using that equation. That's another option. Okay? And again, you don't need the mass for that either. Okay? So that height should be around 40. Okay? All of your answers on number 1 should have a 5 in them.
And which one?
Number 1. Every answer on number 1 should have a 5. Yes.
On 5F, I'm trying to do kinematic equations. Are you able to do that? Because it doesn't get a good GPA.
Well, you can, but you have to watch the signs.
Okay.
So yeah, you're going to use v squared equals v naught squared plus 2ab.
Uh-huh. Feels
Okay.
stupid.
Now, think this through. On 5, determine the initial velocity of the ball so it strikes around with velocity 7.5. So you're trying to find v naught.
Mm-hmm.
Okay? Now, is v naught going to be bigger or smaller than 7.5?
Smaller.
Has to be smaller, right? Because it's going to be speeding up. So the whole key to that one is just you have to watch the signs of your displacement and your acceleration.
Okay.
So yeah, that's the only way you can do that, is use the kinematic equations.
Okay. I must just be doing something wrong because I'm getting like 1.3. And you said it would be a good GPA.
Yeah, and that's not. That's not. Are you squaring the 7.5?
Yeah.
You're doing something wrong. Okay,
You're really good at the ECT side. Yeah. I do one thing good.
great.
Can
Okay, that'll look good on a college resume. What do? I take the ACT really well.
Oh, I'm so dumb.
And you're fast.
True. So dumb.
You
Never
didn't
mind.
even need to apply.
Did you figure it
I
out?
was dividing every single part of it to AD instead of just
Yeah,
subtracting.
you can do that.
Oops.
No, that's
That's what I
terrible.
did.
Yeah, look at the units. How would that work out for you? Okay, Luke,
Can you explain the Y part in C and 8?
on C, Y?
Yeah.
Okay, here's what. Momentum is mass times velocity, right?
Yep.
So if I double the velocity, what happens to my momentum?
It doubles.
It doubles. Kinetic energy is 1/2 mv squared.
Yeah.
If I double my velocity here, what happens to my kinetic energy?
It quadruples.
That's why.
Uh,
Because the velocity is squared in that kinetic energy equation. So it's like a quadratic function, or exponential, I should say. Aiden?
Is it just a coincidence that the difference between the two is the same as the momentum, or is there some sort of correlation there?
It was just kind of random.
Alright, I wasn't sure.
Now, if you've done calculus, you take the derivative of your kinetic energy equation, you get momentum. Once you do calculus, that'll make sense later on. So, huh?
We got that together next semester.
Oh, no. Okay.
On 4F, I just said the object must be speeding up or slowing down. Is that?
Their momentum
Or should we
is
talk
the
about
opposite,
force?
but their kinetic
That's
will be
fine.
different.
Okay.
I'll
Oh,
give
we
you
need
that.
to ask about 4E. On 4E,
What about it?
it's asking about what the force, what physical quantity is given by the slope of the momentum time graph.
Yeah,
Yeah,
I feel like she's gonna sign C-tech teacher. Have you
that's,
notes before
that's
you
Newton seconds over seconds, right?
yeah.
Okay.
were you
Right,
writing
change
anything?
that, yeah. Wait, well, this
Which
is
gives you what?
Newton's
Yes, which is,
force.
there you go.
Yeah. Okay, perfect. So E is force? Yeah, force on acceleration.
Kels, it's Newton seconds. Momentum is Newton seconds, right?
Yes.
This is seconds. So if you change in Y or change in X,
You get Newtons.
you get Newtons.
Thanks, Bert.
That's why I make the big one. Okay. Anything else? Dear Lord, going once, going twice, so on. Okay. So give that hand in. Where you going? Action.
Didn't even make it in the camera frame.
Okay. All right. So the cool thing about how we're going to start off with springs is that if you go back to the very first lab that you all did, okay,
It was a spring.
it was the springs lab, okay? And at the very beginning, we were talking about independent, dependent variables. And you took like a 1 kilogram mass and you hung it from the spring. And I said, take 1 kilogram and multiply it by 9.8 meters per second squared. And you all going, okay, whatever, it's a number, we'll multiply it, right? And you all drew a graph and you put force on here and you put elongation along this axis. So at the time, back when you were physics newbies, why did we put force on the x-axis and elongation on the y-axis?
Because force is the independent.
Yeah, force was the independent variable and elongation was dependent upon force, right? And you drew a line of best fit and you said, "Ooh, we're doing physics, okay, right?
Whoa.
Right?
We were doing physics. We were doing
Yeah.
physics.
And now, at the time, you're going, why 9.8? Now you can actually calculate, oh, now we can use little g equals big G mass of the Earth over r squared, and we can calculate little g, you know, oh, it's a gravitational field, and it's all this cool stuff. So,
Where we've come, guys.
with springs, we're going to revisit this concept. Okay, so like tomorrow, y'all are going to do a lab on springs. But when you're talking about energy, number one, look at it from this perspective. is that when I stretch that spring, do I do work?
Yes.
Yeah.
Yes. Why?
Because it's force over a distance.
It's force over the distance, right? Okay. Energy, go, boom, okay. So, right, you did work, because guess what? If I don't do any work, guess what?
It don't move.
It doesn't stretch. Now, but here's the odd thing about springs, is that if I only put a 1/2 kilogram mass on there, right? It doesn't stretch as far, so I don't do as much work, right? So the more I want to stretch it, the more force that I have to exert. So when you do graphs for energy, and you'll see why this works in just a second, we've got to switch it up, okay? We've got to put force on the y-axis and elongation on the x-axis. That's the first shift that you have to make, because this is the only way the units will work out. So let's say that I put a 1/2 kilogram mass, okay, 1/2 kilogram weighs what? If I take 0.5 times 9.8, you get 4.9, okay? So this is going to stretch at maybe like 0.05 meters. And that's going to be 4.9 newtons. Now, if I double the force by putting a 1 kilogram mass on there, now I'm exerting 9.8 newtons of force, and it's going to stretch to a distance of 0.1 meters. We can draw this line, and we get this nice linear function, okay? So here's what's going to be important. With springs, if you want to stretch it twice as far, you have to apply twice the force, okay? So this is a force distance graph, but here's what's going to be different from the force distance graphs you all have done so far. The force distance graphs you all have done so far have been rectangles, because we've exerted the same amount of force over the same distance, okay? With springs, it isn't. With springs, you actually get like a rectangle shape, okay? So with this, what we can't do with springs is that we can't take force times distance to calculate work, because this isn't a rectangle. But how do you find the area of a triangle?
1/2 base times
1/2 base times height. So the idea is there that the area underneath this line is going to get us our work, but we just can't take force times distance because it's not a rectangle, it's a triangle. Now, so at this point, I could find the slope of this line, right? So I know that's 9.8 newtons, 0.10 meters, and I can use 0, 0 as my other
We
point,
can't see.
okay? Really?
Yeah.
Every once in a while, it just decides to flip out.
Me too. Just see him going crazy over here.
And today happened to be the day.
Is this a school iPad?
Yeah.
That's fine.
Yeah.
I don't know how people got Fortnite on Miss Hammond's iPads. I swear to God, it was on every
Miss
single
Hammond's
one.
class was
photo booth.
interesting.
They had plenty of time to figure that one out. That was a few years ago.
It's not like they were doing anything else in class.
I remember John Shard stepping our back.
Yeah, I sat right in between him
I
and
know.
Nico.
I just stared over that
Because
corner.
I showed up late. I was the last person in, and I was the
I
last
don't know why,
slot.
but now it just works again. Okay,
I was trapped.
so here are the points that I've got. 9.8 newtons, 0.10 meters. I'm going to use 0, 0 as my other set of points, okay? So at this point, I can find the slope of that line doing change in y over change in x, right? So I'm going to take 9.8 newtons minus 0 divided by 0.10 meters. So, Mr. ACT, if I take 9.8 and divide it by 0.1, what do I get?
98.
98. Now, what units do I have?
You know what this one? What was that? Sorry.
What units do I have?
That's.
Do not make this difficult.
Hold on. A Newton is kilogram.
Do not make this
Am
difficult.
I going crazy?
Look at
How about newtons per meter?
Oh. Oh.
Good job, guys.
Am I going
Thank
crazy?
you.
Yeah, you kind of are.
I was like,
I said, don't make it difficult. What did you do?
made it
Made it
difficult.
difficult. Okay? Now, the slope of this line is what we call K. And K stands for the spring constant. And that changes depending upon the string, or the spring. So don't look at this and go, oh, 98 is the same for every spring. No, it depends upon the spring. But here's what's important, is that if I were to stretch this spring 1 meter, I would have to apply 98 newtons of force to it. Now, like if it was a heavier spring, that might be like 5,000, okay? Like a spring on your car, might be like 5,000 newtons to stretch it 1 meter. If it was a really lightweight spring, that might be like 1 newton per meter. So this changes depending upon the spring. But the bigger the number, the bigger this number, the harder it is to get that spring to stretch. Okay, so that's the main idea. So here's the deal. So what we're going to do is we're going to find the area underneath this graph, right? So we know our spring constant, okay? So that's going to be the slope of that line. So because it's a linear function, we can do y equals mx plus b. So finding the area is going to be easier because there is no y-intercept. So on spring graphs, y-intercept is going to be 0 because if I don't apply a force, I don't have any elongation. So I only get an elongation if I apply a force, okay? If I don't apply a force, I don't have an elongation. The more force I apply, the bigger the elongation becomes. So, on this one, we graph F, force on the y-axis, so we're going to put that as force. We just said m is the slope, which is going to be that k value, and x is going to be our elongation. So if you look on your equation sheet, on the force section, you have this right here. It's about halfway down. It says FSP equals F equals KX. So this is the force that it takes to stretch a spring. K is the slope, X is how far it stretches, F is how much force it takes to make that happen. Okay? So F equals KX. That's the slope of the line. So if you go and try and find the area of this, right? We have force and we had elongation. And that was 0.10 meters. And that was 9.8 newtons. Okay? So Kels, do I have enough information to find that area?
Yes.
What are you going to do?
1/2.
Area equals
1/2.
base times height, right? So that's going to be 1/2 times my base, which is 0.10 meters, times the height of, what?
9.8.
9.8 newtons. Now, what units do we get?
Newton meters.
Newton meters, otherwise known as, rhymes with ools,
Joules.
joules, right? Which is a measure of work, which is a measure of energy, okay? So the area underneath this graph is going to get us the work that's done in stretching the spring, okay? So somebody take 0.1 times 9.8 and take half of that, and you should get 0.49, and you can either put Newton meters or you could put 0.49 joules. Now, here's what's important on a spring graph. If it's like me just pushing this thing along, okay, I'm applying a constant force over a distance. If it's a constant force over a distance, that area is, or the work, is going to be force times distance, and that's just the area of a rectangle. Okay, so if it's the same force over a distance, you can just do force times distance. This is going to be a rectangle. On a spring, because it's a sloping line, we're still finding the area, but this is why we have to have this 1/2 in front of it, because we're only finding the area of a triangle, not the area of a rectangle. Okay? So on springs, you can't do force times distance. You have to put the 1/2 because you're finding that area. Okay. Now we're going to do a little bit of voodoo. Okay? Just a little bit. So if you look at what we just did, we took 1/2 the base, which is elongation, right? And we multiplied that by the force. Okay? That's what we did. Now, but up here we said, because this is a linear function, that f equals kx. So I'm going to come in here and go, okay, that's 1/2 x times kx. So all I did was I took kx and I substituted that in there for force. Okay, that's all I did. Now, area, we just said was going to equal work, which is going to be the amount of energy that I store in the spring, which is going to be 1/2 kx squared. So down here on towards the bottom of your equation sheet, you have energy stored in the spring, which is going to be 1/2 kx squared. Okay? So here's the deal. Because the x is squared, Luke, if I double the distance, what's going to happen to the energy that I'm going to store? It's going to quadruple it. But F equals kx. If I double the distance that I'm going to stretch it, what's going to happen to the amount of force that I have to apply?
Double.
That's going to double. So, for just historically, kids tend to get this mixed up. So, when you're talking force, that's kx. When you're talking energy, that's 1/2 kx squared. Okay? So, make a mental note, say, oh, right, we're dealing with two different things. They're related, but they're not the same thing. Okay? So, if I double my distance, I quadruple the energy that I store. If I double the distance, I double the amount of force that I have to apply. Okay? So force gets doubled, energy gets quadrupled. Okay? If you double the distance. Cool with that? Okay. Now, where'd my red card go? Stop that for a second. I've lost my red card.
I did actually Gavin right.
Okay.
Oh my God.
So now we're going to throw. Now we're going to throw springs into the mix, okay? So, and again,
We're done.
okay. So this is also going to go old school, because remember back when we were just studying position time graphs and velocity time graphs, and you did the lab when you pushed it against the wall and it hit and it bounced back, and you had to draw like the position time graphs and the velocity time graphs, and you go, oh my God, this is so difficult, right? Okay?
100%.
Well,
Now we have to figure out this.
some of us have.
No, because I actually thought that.
Okay, I know you. Okay, so now we're going to revisit that lab, okay? So, when this thing is rolling along, what's the only type of energy that it has? Kinetic, right? Now, it's going to roll along, it's going to hit a wall. It's going to hit that wall, and that spring is going to begin to compress. So as that spring compresses, right, what's going to happen to the potential energy stored in the spring? It increases. But what's going to happen to the kinetic energy of the cart? It decreases. So this spring is like horizontal gravity. Okay? Going, no. Because if you think about it, it is. So if I throw this thing up in the air, right, I transfer kinetic energy into okay, potential energy. If I use a spring, I take kinetic energy and change it into us. Okay? If I throw it up, I change it into if I roll it this way, I change the kinetic energy into us. Okay? Right? Got that? Okay. So, here's the deal. I've got this cart, it's rolling along, it has a mass of 0.3 kilograms. It's moving at 2.5 meters per second. Just knowing that, what can we determine? What'd you say?
Elongation?
Kinetic
I
energy.
don't know.
The kinetic energy, right? Because kinetic energy is 1/2
Thank you.
mv squared. So as it's rolling, what's the only type of energy that it has?
Kinetic.
Kinetic. Now, when it hits that spring, that kinetic energy is going to begin to, I'll use the Lily thing, the kinetic energy is going to,
Decrease.
but the potential energy of the spring is going to increase, right? Now, when it's fully stopped, how much kinetic energy does it have? Zero. Has no kinetic energy. But all of that kinetic energy that I had is stored as potential energy in the spring. So that's like if I throw this thing up in the air, when it reaches its maximum height, the kinetic energy that I had here equals the potential energy at the top. Okay? So this is going to be like horizontal gravity. Okay? It's going to slow it down, stop it, and then it's going to speed it back up. Okay? Got that idea? All right. So, oddly enough, I want to set up a chart.
Let's see if I can understand this too.
Okay? Now, what's the only two types of energy I'm going to have?
Kinetic energy.
Kinetic energy and us. Am I going to have us or am I going to have ugh? Us. So let's talk about us. Words any guy hates to hear. Let's talk about us. No, let's not. So we can have kinetic energy, we can have us, and we're going to have like the sun, right? So initially, how much us is there? Zero. We have no us. Okay? We're O for us. Do I have enough information to calculate the kinetic energy? Yes, because I know mass and I know velocity. Okay. So kinetic energy is going to 1/2 mv squared. So somebody take 1/2 times that mass of 0.3 kilograms times that velocity of 2.5 meters per second squared. So it's 0.3, which is the mass, times 2.5 meters per second, which is the velocity. When we square that, that's going to give us that kinetic energy. So what do you get out of that?
0.938.
So call it 0.94.
Okay.
Okay? So I've got 0.94 joules of kinetic energy. So now, what's my sum going to equal?
0.94.
0.94. Now, guess what? Everything at any point has to add up to 0.94. Okay? That's why you have to have that bottom number right, because that tells us how much energy is in the system. The only thing I can do is just change the form of it. Okay? Cool with this? Now, the first thing I want to figure out is how much kinetic energy and what's the velocity after the spring has compressed 0.01 meters. So conceptually, this would be the similar type of situation of what we did yesterday. Yesterday I said, hey, I'm going to throw a ball up in the air. I want to know what's going to happen when it's 1 meter above the ground. Okay? This is going to be the same idea. This cart is going to go along. I want to know what's going to happen when that spring has been compressed 1 centimeter or 0.01. Not very much compression, right? But it's going to compress a little bit. So it's the same idea, okay? Instead of storing it as UG, we're going to store it energy as in the spring, okay? Got that idea?
Yes.
So, this is when it was rolling, right? And it was all kinetic energy and we didn't have any us. Now, what I'm going to do on the next part, I'm going to say, okay, what's going to happen when it compresses 0.1 meters? So obviously, what's going to happen to my kinetic energy?
Decrease.
It's going to decrease. What's going to happen to my us?
Increase.
It's going to increase. So do I have enough capacity or information at this point to calculate us? Yes, because I've got the spring constant, okay, 3.00 times 10 to the third newtons per meter, right? I've got that number. I know how far it gets compressed, so I can calculate us. So I go us equals 1/2 k x squared, right? Now, it doesn't make any difference if you compress a spring or if you stretch a spring, okay? It's still the exact same equation. You're still storing energy. You either store it by making it expand, or you store it by compressing it, okay? Either one's the same equation. So in this situation, somebody take 1/2 times 3.00 times 10 to the third newtons per meter times 0.01 meters squared. Let me know what you get.
Got 0.15.
0. What?
15.
Beautiful.
Is that what you got, Lil?
Yep.
Okay.
Okay? So that's how much potential energy I've stored in the spring. So of these 0.94 joules, how much of it has changed into us? 0.15, right? So how much energy is going to remain as kinetic?
0.79.
The difference between those two, which is
0.79.
0.79 joules. Okay? Makes sense. Okay? Good. So, at this point, I have remaining kinetic energy of 0.79 joules. So how can I use that to determine the velocity?
Kinetic energy?
Well, kinetic energy equals 1/2
Mass velocity.
mv squared.
mv squared, right? So who solved it for velocity yesterday? Was that? Okay, so what's the Bender equation? Velocity is the square root of 2k over m, right? So we're going to take 2 times 0.79 joules and divide that by the mass. What was the mass?
0.30.
0.3 kilograms. Okay? So, this is how much kinetic energy that I've got left over. So, now what does my velocity have to be less than?
Starting velocity.
Yeah, my initial velocity was 2.5, so this answer has to be less than 2.5. If I get an answer bigger than 2.5, I've created energy. So what do you get?
2.29.
2.29, okay? So we've slowed down a little bit, but not very much, okay? Good so far. Got it. Now, here's the next step. I want to find maximum compression. So in other words, when this cart is completely stopped, okay? When this cart is completely stopped, how far is that spring compressed? Now, here's the deal. That's the same idea as if I take this cart and I throw it up in the air. So if I take that cart and I throw it up in the air and say, hey, what's the maximum height? Well, at maximum height, how much kinetic energy do you have?
0.
0, because it's all
Potential.
potential. When this cart has stopped, how much kinetic energy do I have?
0.
Because it's all stored as
Spring.
spring energy, right? It's all us. So, under maximum compression, if you go back to your chart, right? So under maximum compression, how much kinetic energy do you have?
0.
0. How much us do you have?
0.94.
0.94. Because the sum is still going to be 0.94 joules. Oh, that's kind of cool, right? So, us, if we talk about us, is 1/2 k x squared. So what's the only thing I don't know? X. So Luke, how am I going to get x by itself?
And then multiply by 2,
So I got 2us.
and then divide by k, and then square root that.
Beautiful. So I'm going to take 2 times 0.94 joules divide that by the spring constant of 3.00 times 10 to the third newtons per meter. So what do you get now? What does this answer have to be bigger than? Well, when we did 0.01, it was still moving, right? So my answer has to be bigger than 0.01. So what do you get?
0.025.
What'd you get, dear?
0.025.
0.025 meters. So which is about 2.5, right? So at point, because I know my answer had to be bigger than 0.01. Oh, it's bigger, it's 0.025. Okay? Now, here's the other reason why when you draw your graph, if you look at us equaling 1/2 kx squared, the units of k has to be newtons per meter. This is not newton meters. If it's newton meters, it's joules. This is newtons per meter. The reason that it has to be newtons per meter is that x is going to be meters squared. You cancel out one of those, then you get newton meters left over, then you get joules. Okay? So that's why when you draw this graph, you have to put elongation on the y-axis, excuse me, force on the y-axis and elongation on the x-axis. Okay? Now, here's how you could throw a new twist into this. Okay? You could say it's rolling along, it's going to hit this, it's going to bounce back. Now, if we don't lose any energy, at all, it's going to bounce back at 2.5 meters per second. So here's what you could do to the next step on this. Okay, it rolls along, it's going to hit the wall, it's going to bounce back, then it's going to roll up a hill. So now, when it rolls up the hill, at its highest point as it rolls up the hill, how much gravitational potential energy would it have?
The same amount.
The same amount, 0.94 joules, right? So then you could find the height that it would roll up the hill. Or you could reverse it and say, okay, it's going to start up a hill, it's going to roll down, it's going to become kinetic energy, and then it's going to turn into potential energy in the spring. Okay? Got the idea. So it's all about the charts. So stop that.
It's going back up the hill with more energy.
Okay. So when you get to number 4, okay, you're going to draw a simple graph. You don't have to draw on a graph paper unless you want to. You're just going to come over here and you're going to make a simple graph of this spring. Now, here's the deal. Listen to me. You plot elongation versus force. It's not length of the spring versus force, okay? So it stretches, it's 5.6, then you're going to add a weight to it and it's going to stretch to 15.6. So how much did it stretch?
The difference.
Between 15.6 and 5.6, which is 10, okay? So you want to use the 10 centimeters as meters as your elongation and then the force, okay? Keep that in mind. You're not plotting length of the spring, you're plotting elongation. You're going to find the slope of the line. Anytime you have a graph like this, you cannot use work equals force times distance because it's not a rectangle. You have to treat it as a triangle, okay? So on number 4, do not use work equals force times distance because we're not applying the same force over that distance. When you get to number 6, I don't know why, but when I was typing the question, purple seemed like a good idea. So you have a box of purple crayons, it's sliding along, hits a spring. So number 6 is just like the problem that I just worked. Set up a chart. 7 is the same idea. You have Jerry and the skateboard. And this, for whatever reason, a mouse sounded like a good idea. So on number 7, here's your visual. Here's the little skateboard. And there's Jerry the mouse, okay, right? And they're moving along. So what's the only type of energy that they have?
Kinetic.
Kinetic. Now, it's going to go on number 7, you're going to have 3 types of energy. You're going to have kinetic, you're going to have UG, and you're going to have US. So when you set up your chart, have all 3 of those values. Now, when you get to number 8, here's this bridge. And if you've ever seen bungee jumping, people fall and,
True. They do fall.
They do.
yeah, they fall. And, hold on, I've lost Al.
Is he on the ground? Is that who Al is?
Oh,
Oh.
Okay. So, here's the simulation. So, you're up here, you've got the bungee cord.
The hair kills
You're gonna fall, but you're gonna be in free fall, and then the cord is gonna begin to stretch. Now, up here, you're here, you fall, and then you stretch the cord, okay? So what's happening here on this one, let me kind of give you the visual. You have an unlength stretch of cord of 12 meters. So what that means is that you're gonna fall 12 meters before the cord begins to stretch, okay? You're gonna fall 12 meters. You're going to end up a total distance of 31 meters below the bridge. So if this is 31 and that's 12, how far did you actually stretch the cord?
43.
Huh?
43, right?
The
What?
total length is 31,
19.
19,
Oh. My bad.
okay? So that's gonna be how far the cord is going to stretch. So the first thing that you wanna do is find the value of K. So here's what you wanna do. Reverse the process. Imagine that you're down here and you're gonna be lifted up to a height of 31 meters. Oh, that's gonna create a lot of UG, right? So that UG is gonna be MGH. Now, that has to equal the energy that you store in stretching the spring. That's gonna be 1/2 kx squared. So this is what, on that first problem, oh, speaking of potential energy. So you know all of this. You know mass of the person, you know G, you know that's 31 meters. You know X, which is going to be 19, because that's how far the spring stretches. Solve that for K. And you should get around 100. So your answer to 8A, no, excuse me, 8B. 8B should be around 100. Okay, I'm done. You're on your own. I go check on the printout that I just forgot about, and I'll be right back.